Hello everyone, and this is page 5 of our IB past papers. This one's from 2018, and it's standard level May, and page 5 gives us question 8 and 9. So here we go with question 8. Distances between successive points on a moving car measured at equal time intervals are shown. So what this means is that a car is going to start, obviously over here on the left of the page, and if you imagine there's a mark that is given by these dots let's just say every second. So it starts here, it's going to go tick. As it moves, it's going to go 1, 2, 3, these are the seconds, 4, 5, 6, 7 seconds. So these dots that we're making here are evenly spaced in terms of time, but obviously the gap between them is increasing. So we need to figure out what's going on here, the type of motion. We need to figure out whether it's accelerating. The acceleration is increasing linearly with time. The acceleration increases non-linearly with time, whether it's going at a constant speed or a constant acceleration. So what I would do, if this was a lab, I would get us to measure these, but rather than measuring the distance between each dot, I would go ahead and make this cumulative. So I would measure this distance here, which would be 1. Then I would measure this distance here, which would be 2.5. Actually, let's write these in. So this is going to be 1, then 2.5. Then let's keep going to here. This is going to be 4.5. And then we'll keep going to here. Each time I'm going all the way back to the beginning, all the way to here. So this is 4.5 and that makes it 7. And then from the beginning once again, all the way to here. This is going to make it 10. And then the last one all the way to here is going to give us 13.5. And then let's just make up a number. Let's say that each one of these is 1 second. So it's 1 second. Oops, that wasn't very good. 1 second, and then 2 seconds, and then 3 seconds, and then 4 seconds, and then 5 seconds, and then 6 seconds. Okay, each dot, that's representing each of these dots. So the first dot is 0. 2, 3, 4. There we go. Like that. Okay, and then we could potentially do a little table here and then plot it. So let's say that I've got a table, and on the x-axis is going to be time, and on the y-axis is going to be displacement. Okay, so let's put these in, and then we can get ourselves a little bit of a graph, and things might come together. So at 0 time, we'll say that it's traveled 0 distance. At 1 second, that's going to be 1 second is here. It will have traveled 1 unit. Let's say 1 meter. These are in meters and seconds. Here we go. Okay, let's keep going. At 2 seconds, it's going to have traveled 2.5. At 3 seconds, it's going to travel 4.5. At 4 seconds, it's going to have traveled 7. At 5 seconds, it would have traveled 10. And then at 6 seconds, it will have traveled 13.5. I just realized I wrote the wrong thing. So let's change that. That's going to be 6 seconds. There we go. All right, so we're going to make a little bit of a sketch graph here. Nothing fancy. We're going to have our x and our y. Actually, let's make it a bit bigger. Let's make it bigger. Let's go like this. And we're going to have 0, and then 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, 6 seconds. Let's put this in. 1, 2, 3, 4, 5, 6. These are all in seconds. This is time. And then on the side, we have displacement. displacement. And then what have we got? We're up to 13, so something like that, going up in 2s. Just a rough sketch. Okay, let's put some data in. Let's have a look. 0, obviously we're going to have 0, put a little cross there. 1, we're going to have 1, so it's going to be somewhere there. 2 is 2.5, so somewhere there. 3 is 4.5, so there. 4 and 7 gets me to about there. 5 and 10, we're all the way up here. And 6 and 13.5, so all the way up here. Now, hopefully you can see what's happening with this graph, and if it wasn't clear from the very beginning, what's happening is that this graph is curving upwards. It's going exponentially up. That's not a very good line of best fit, but you get the idea. So if we were to take a tangent line, what would this tell us? Let's take a ruler and see if we can get a rough tangent somewhere about here. Let's just take it here. We'll put a tangent line in here. This is going to give us the slope of this moment on the graph. Let's go there. And the moment on the graph is, let's just say it's about here. Well, the slope of this graph is displacement, okay, in other words, the distance over time, d over t, which is velocity. Okay, and so this slope here is not very big. It's not a steep slope. But if I come up to if I go further along in time as the car is traveling, and I take my tangent line up here somewhere, and I put that in, is this slope here steeper? Yes, it is. So this slope here means that the velocity is bigger here, and the velocity is smaller here. So in other words, there's been a change. There's been a change in velocity between here and here. It's increased, and it appears to be increasing at a sort of continual rate, which means, and you've all guessed it by now, is that this car is accelerating uniformly. It's uniform acceleration. I can tell that just by the graph. This is uniform acceleration. So it's got to be D. Okay, so for question 9, we're going to need a couple of formulas again. So here's our datasheet snippet. We'll just pop this up here. Yeah, we'll leave that up there for now. Hopefully you can see. Maybe I'll make this a bit smaller. There we go. I think that's everything we need. Okay, so we have an object moving in a straight line. Here it is. Clearly it's moving to the right. And the reason it's moving to the right is because we have an applied force, capital F, and a resistive force, probably force of friction, to the left. So that means if we were to do a net force, then we would see that the force net, and this is not to scale, the force net is going to be this way, which means it's going to accelerate this way. It's going to accelerate this way. Oh, let's get my pen working. There we go. It's accelerating this way, etc. So we can say a couple of things about it. We can talk about the momentum, the change in momentum. It's going to be accelerating, so there's a change. This might happen for a period of time, which we don't know. There's a time frame around this. We can talk about the Newton's second law, F equals ma. We certainly want to start thinking about this as an F net. So we're going to do a little sum of all the forces calculation, because ultimately we're going to be asked to give an answer in sort of algebraic form, and we got to be, oh, there's the time. Both forces act as a time. We've got to read this really carefully because it's asking what is the rate. Okay, so whenever you see the rate, hopefully you're thinking like this. You're saying the rate is always going to be some value divided by a time, right? It might be rate of acceleration, the rate of change, whatever that might be. Normally they're dividing it by a time frame. So this is a key word. What is the rate of change of momentum? So what does that mean? Well, change of momentum, that's over here, isn't it? Delta P. So delta P is, well, it's F delta T, but it's going to be F net, isn't it? With regards to this example, it's the F net times the change in T. And more importantly, because we've identified this rate issue, it's going to be the change in momentum over a period of time. So that's kind of what we're looking for. So let's look at our F net expression here. The F net, let's treat this way to be positive and this way to be negative as convention. We're going to say that the F net, oops, can't write, there we go, F net is capital F plus a negative F. So in other words, the F net is F minus F. Okay, let's bring that over here. Let's put that in. So we're going to say the F net, which is F minus F multiplied by T. And now we have to take care of this rate. Okay, so this here, this expression, F minus F times T, this is delta P, but we need to do delta P divided by time because that was our rate. I'm going to add that into my previous statement here, divided by T, because we're talking about a rate. And that's in the question. So to get that, I'm going to divide this by T, and of course that cancels out. And that leaves us with just F minus F, which means the answer is B.